All right. Hello, my friends. Welcome. My name is Seth Juarez. I'm super excited to be here. I would never miss an NDC if I had to. And so I'm super glad I could be here. Good afternoon to all of you. If you're in the UK and whatever time zone you're in, good morning, good evening, and good night. I'm excited to start to talk today about getting started with computer vision. It's a fun topic. We've got about an hour, and I've got content for about maybe 45, 50 minutes, maybe. But the reality is I got over here. I have if I look over, I'm looking at the folks that are here, number one. Number two, I have the chat open both on WebEx as well as on the Slack. And so just pop in the questions as we go. If you want, if you are like, hey, if you'd like to go unmuted, that's cool too. Just say, hey, can I go on unmute and ask you a question? And I would be delighted to answer those questions. If there's a problem or you're not seeing something, please let me know. The cool thing about this is I can show you everything on my screen and you can see it completely clearly, and you can hopefully hear me really well as well. But again, those are the instructions. Please, 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 please. You can pop in the questions whenever you like, which is super cool. And again, like I said, I have track one open over here on Slack as well as the WebEx chat. All right, so I think we should start getting started with computer vision. The problem often with machine learning and AI in general is it kind of feels like yeah, let me get my there you go. It kind of feels, oh geez, my settings, that's not what I wanted. Thank you. It kind of feels like when you're given instructions on what it is you need to be doing with AI, it's like it's really too easy two-step thing. First, you got to draw a couple of circles, and then when you're done, you just fill in the rest. This is what it feels like when people talk about AI, like from a marketing perspective, and sometimes even from a technical perspective. Today we're gonna try to. I'm doing the same thing. I'm gonna be like, hey, you can do AI in 3 easy steps. I'm doing the same thing, but I'm actually gonna show you how it works, what's inside, and what's going on. And it turns out this is an interesting article. 40% of AI startups in Europe have almost nothing to do with AI. Just to give you a sense, and this was published a year or so ago, almost 2 years ago. Holy cow! I wonder if that percentage still holds. I'm not sure. So what we're gonna do is we're gonna talk about like what is this thing? When is it a good, because as a programmer we have this sense of like when it's a good idea to use certain techniques. I'm going to give you a horse sense for understanding when AI or machine learning is a good use, when it's the right tool, and then I'll give you a way to divide up the space in a way that makes it more understandable. We'll get to like what it means from a programmer's perspective. My background is I started as a programmer. I did .NET Dev for 10 years. And then I went to grad school for AI and machine learning. And then I understood all the new concepts in terms of the programming concepts. So we'll do that. And then we're going to apply it to something where machine learning is actually really quite good. And that's computer vision. And we're going to build out something that looks kind of good. I've already built a lot of it out because you don't want to see me typing too much. I guess you can if you want. And I'll show you how I built out something that does something similar to the rock, paper, scissors game. So that's what we're going to do. So let's talk about, and again, questions all in the chat. I'm happy to answer them. Okay. Close this window. So what is this anyways? When we talk about artificial intelligence, imagine it as this huge bubble. And I know bubble is not the right thing when it comes to like tech. You don't want to say bubble, but imagine it's this artificial intelligence. It's this really big thing. And it turns out that when we're talking about artificial intelligence, it's actually any algorithm or computer program that makes it look like the computer is smart. Computers, don't have intelligence. They're not smart. They just carry out a bunch of instructions or recipes. But that's different from things like machine learning and deep learning. So I want to show you what these all are and what their differences are. Artificial intelligence composes all of these things, machine learning and deep learning. But in regular artificial intelligence, this stuff you can trace back all the way to like the 1950s. So it's quite old. It's not new. And if you've ever played like a game like chess or tic-tac-toe against a computer and it feels like it's smart, or you've ever like had a computer like find something that was seemingly complex, the artificial intelligence of yesteryear was something that I like to think of as intelligent search. I'll put intelligent search. So, for example, if you've ever used Waze or some program that lets you find the fastest way to get somewhere, these things use a variance of algorithms called A star. And what they do is they create a world in which you're a node and you have some edges and you're trying to find the fastest path. And A star does this intelligently through what are called heuristic functions. They're really smart. If you've ever played a game against a computer like tic-tac-toe, you probably run into something that is a variant of algorithms called minimax. And what they do is they look at a move that you make. They look at a move that you make, the state of the world, and they say, what are all the moves that that I can make? And then they enumerate them. And then they're like, what are all the moves that my opponent can make if I make? And then it creates this huge tree. And basically, Minimax searches through them, right? There's some smart algorithms that do like alpha beta pruning of the tree because the tree can get quite large when it comes to games like chess. But when it comes to games like tic-tac-toe, you can actually enumerate the entire search space completely. So I can get a computer to look at every move that I make, every move that you make, every move that until the game is over, and I can search a path. And it turns out that I can make a computer always win or draw against you every single time just by searching this tree. And so this is what artificial intelligence was a long time ago. We still use these algorithms today, by the way. If you're looking at trying to make an intelligent program, think about it in terms of, can I make it into a finite search space? If I can, then I can use some techniques for searching it. Now, it turns out that there's certain programs where that's not the case. For example, give it a picture of me like doing this, and then it's saying paper or this, and it's saying scissors or this. That's a little bit harder because that search space is a lot larger, because we've got to make it work for all the pictures of all the people doing those symbols. And it's hard to come up in our brain with an algorithm, and we'll come up with an illustration in a little bit. So machine learning is a process whereby instead of intelligently searching this space, we give it examples of the right thing, and it comes up with a way of solving it, right? And so a good example of some machine learning algorithms that you may have heard of are, for example, linear regression, which does that. You give it data, and it comes up with a function that it can do. You've probably heard of classifiers such as naive Bayes, or SVMs, or decision trees, or neural networks. And notice that these are all things that exist to produce an output such that when you give it a future example, it figures it out. So this is cool because you're giving examples. This is different. This is not the same as this one, right? Because this one here searches a space. This one here, you give it examples of the right thing, and then it figures it out. Now, deep learning is interesting, right? Because deep learning is actually neural networks plus. And this here, like, when does it graduate to neural networks plus? Depends on the marketing guy. Because neural networks, deep learning is basically neural networks, but with more neural networks in it. So that's the interesting bit. So hopefully this is helpful. It's a good way of understanding the separation between all of these things. So let's see. Okay, cool. So the question is, when should I use it? And this is the $1 million question. And as programmers, we get this, how do I put it? We get this hoarse sense about, like, when I should use a certain technique. Like, should I use object-oriented programming, or is functional programming the best, or what kind of data structure should I use? We get this sense for like, this feels like a linked list, or oh, this feels like I should use a dictionary, or what I'm saying. So I'm gonna hopefully help us understand. Like, you're gonna feel your brain break, and you're gonna know that when you feel your brain breaking that way, that's when you should use AI. So, and I'm going to use an example from a check, like a bank check. And I know we don't use these anymore, but I think it's still a good example. So I'm going to do it. So does anyone work at a bank? Any bank? Okay, so programmers at banks are like, in America, we have this show called Dirty Jobs, where it's like the guy goes and cleans the sewer. Like, programmers at banks are like the dirty jobs of programmers, at banks. Not because banks are necessarily inherently evil, although some are, but because like the garbage data that they work with has got to be really ridiculous. Like, Phil in the back is always putting like name in the age field because it's COBOL and you can, right? And they got to fix that. So let's suppose for a second you're a crack programmer, Sally. You're the best programmer at the bank, and it's a small bank. And you're the best programmer they have because Sally is a genius. And Phil from marketing comes down. He's like, hey, so I have a really good idea. And Sally's like, okay, what is it? So picture this. Imagine a scenario where, because we scan all the checks that people, so that we can store them. I want you to write an algorithm. I want you to write a program, Sally, where you look at the check and you flip it to be right side up every time. And as a programmer, you're like, okay, well, how do I do this? We come up with a series of steps to solve this problem. And so Sally's like, yeah, I can do it. It's going to take a day. It's really going to take 4 hours, but there's a lot of YouTube to watch. YouTube isn't going to watch itself. All this content is getting made, and these are the jokes, people. So she's like, yeah, I can do it. And the reason why she was so confident is because the checks in your bank, because it's a small bank, have this really unsightly black stripe at the top. So in our brains as programmers, we can automatically think, well, if I sample 100 random pixels at the top of the picture and they're not all black, then I know that it's upside down and I flip it. And you're like, okay, I can totally do that. So you get this done in 1 hour, and it's the greatest thing ever since sliced bread. And Phil from marketing is like, that was so good that the bank owner, Phyllis, and if you're a bank owner, you have to have horses. I think it's a rule. And Phyllis has horses, and Phil is like, Phil and Phyllis, I didn't know I did that on purpose. So Phil is like, look, we want to make it so that just this one thing, it's just an easy thing, just one little adjustment. And anytime a marketing person's like, hey, it's this easy one thing, it makes us nervous. So Sally's nervous. We want to make it so that this algorithm also works if Phyllis's horse pictures are on the check. So no ugly black stripe, but Phyllis's horse. So this is a little bit harder. And you're like, all right, it's going to take 2 days, but give me pictures so I can look at it. And so Sally painstakingly goes through and does some pixel analysis and figures out that there's some shading of like dark hoof pictures at the bottom in the middle. And so you do the random sampling thing. There's a lot of if-else statements and for loops, and it's kind of goofy, but you figure it out, and after 2 days it works. You notice how it went from easy to harder, but not impossible? So Phil comes back down the third day and is like, I guess he's like, hey, this is such a hit. Phyllis is so excited. We wanted you to do this for every person, for every picture, for every check. Because now they want customers to put any picture on it. And so hopefully as a programmer, you felt your brain break at that point. How could you possibly effectively write an algorithm such that you can look at any check and figure whether it's upside down? I'm sure you could do it, but it got considerably harder when it changed from a single stripe to a one constant picture to every picture. It is in that mental gap where you can't figure it out, but you can see it. You know when you see it, that's when AI works the best. Because when it comes to programming, this is what we focus on. How do I write this thing? And then how do I make the machine do it such that the answers come out? And in machine learning, we actually flip these. And I want to go back so you can see. I literally flipped it. Because in here now, what we want to do is we want to give it the answers and the input. Oh, man, why does it do that? And then the output is an algorithm. And the question is, well, how does this even happen? In machine learning, let me go back. In machine learning, these have specific terminologies. So when you see it, you'll know what people are saying. So this is called the data, obviously. And this thing is called the model. And this, to me, is analogous to an algorithm that was learned and not programmed. And that's the key. When you hear about machine learning models, that's what those are. And then the question is, well, there's something must be happening in here, because how does it actually do this? So we have options. And for us, there are 3 options that we can take when it comes to pictures, because that's easy. Now, when you think about pictures, and I'll do a little drawing here, so you can, because pictures literally are. Oh man, I'm so bad at drawing. That was crooked. It's like it was leaning over. So it's still leaning over. So a picture is just like a square, and inside of each pixel, right? Let's imagine a little box. There's like 3 numbers, red, green, and blue. And so that's the data we're working with. And you might even have an alpha channel, so it might be 4, but we're not going to consider that. We're just going to say these are solid images, because in reality, when we're looking at humans, we're not like, wow, that's a beautiful alpha channel I see in the picture. You don't see that. We don't look at that, right? We just see the whole thing smushed. And so that's what we're going to give the computer. So this is what we're dealing with, like a big matrix, but 3 times, right? Where each one of these things, this one's like red, this one's like green, and this is like blue. And so basically we're giving this thing to a computer, and it's figuring out some stuff. So let's see. But now that we have this, now that we've done this machine learning bit, everything after this is just programming, like we did before, right? We did something, the model or algorithm came out, we plug that in, and then we give it new input and stuff happens. So for us, this is what we're doing. This is the thing. Oh, look, I'm even wearing this shirt. We're giving it examples of rock, paper, scissors. It produces a model or algorithm, and out comes the thing, and then we give it a new one. We don't know what this is, and it should be rock as it comes out. That's what we're doing. This is what this is all about. So the question is, what are my options for this? So we're going to go through 3 options. The best option for us in this case is the second one, but I still want to show you the third one briefly, because I think it's important. So the first option is you want to just use something or someone already built. A long time ago, I worked for a company called DevExpress. They make data grids, right? I was their program manager over their analytics division. And I remember I was doing booth work one day. Let me get a drink of water here. I was doing booth work one day, and dude comes up to me. He's like, I could totally build a data grid. And I was like, I have no doubt you can build a data grid. In fact, I bet you could build it in a week or 2. And he's like, yeah, you're right. So he's like, so why would I buy it from you, Seth? And I said, that's an excellent question, Bob. I don't know what his name is. I don't remember. And everyone's going to empathize with this. And I said, Bob, it turns out that when you write code, that code stays with you forever. Forever. Some of y'all in here are still helping from that job 3 times ago. Someone calls you up and is like, hey, I know I don't work here anymore, but you made this thing, and I want to know if like you can help us with it. And all you can think about is I've got to go fix that thing for that person because I built this thing 100 years ago and it's still mine. Yeah. And so I said, Bob, is your company in the business of making data grids? And he's like, well, no. I'm like, well, if you write your own, then it will be. And he was like, how much is your license? $1,000. He's like, and we support it forever. And he was like, oh, can I get your card? Yes, you can, Bob. Thank you. This is my favorite story of all, because like every one of you folks can write anything. I have zero doubt. But every one of you folks don't want to support everything. And so that's where pre-built AI comes in. Someone has already built machine learning models that do stuff. And so you can just use them. And they're fairly generic. So let me do this. I'm going to show you here. Let me go to the next one. At Microsoft, and you'll find these everywhere, but at Microsoft, we have these things called Azure Cognitive Services. And it just brings AI. I love this. Cognitive service. I'll read it because I got a new microphone, so I'm supposed to sound like I'm on the radio. I'm going to read it like I'm on the radio. I got it. Hold on. Let me get some background music here. Cognitive Services brings AI within reach of every developer without requiring machine learning expertise. All it takes is an API call to embed the ability to see, hear, speak, search, understand. Yeah, so it's like the data grid that you don't want to build. And there's a number of APIs already that just exist. We are, I promise, the computer vision portion, because that's what we're talking about. So let's just go there. And let me show you what computer vision does. Okay. So let's find a picture here. So we're gonna go to the Twitters and just get the tweets. Here's the tweets. Let me go to this here. Let's see here. Profile. Here's my picture. So we'll open this image in a new tab. There you go. So there's the tweets. So I'll close this and let me move this over. Why is it kind of in the way? We'll close this. And what I'll do is I'm going to put the image URL in here, and let's just analyze the image and see what happens. Let's just call the data grid. Boom. There it is. Notice that just by calling this, we're getting a lot of stuff. First of all, we're getting the objects. Looks like it found two people. There's some tags for it. There's a person. There's it's outdoor. There's a tree. There's a human face. There is some clothing. A woman posing, suit, confidence, people. So these are the tags that you get. So you imagine being able to do that. Now, I'm going to be serious. And I don't know why we don't talk about this feature, because it's awkward to talk about. But it turns out that our AI will also tell you whether this stuff is inappropriate. And for example, and there's an inappropriateness level as well, because in certain cultures, there are things that are inappropriate where other cultures, they're not. And I'm not placing value judgment on any of them, but we will tell you if it's culturally insensitive too. And so that's interesting. Here's a description, all the tags, and it will even come up with a caption. And this is bananas. Seth Juarez et al. Posing for the camera. Now you're probably wondering, how does it know it's you, Seth? That's a good question. So I was giving a talk once with the guy that was in charge of MSR, Microsoft Research. He's since left the company and gone into very famous guy. And I remember doing this demo with him on stage, because I took a picture of me and him for the demo. And the joke was, like, he's famous, so his name is there. And it just said, like, the famous guy and some other guy, which was me. And I just made a joke, like, I'm not famous enough for our computer vision stuff. And so the programmers must have watched it and now they added it in there. And so according to the AI that we have, I am now a celebrity. I think I've made it. I don't know. I've made it. Yeah. Can we get a shout out? Thanks. Thank you. I am now famous, according to some machine learning model. But notice that this, again, is one of the options. But if I were to put a picture, let's see if I can upload a picture. Let me find one here. C projects food. And this is not, I haven't practiced this part yet. Let's go to the data. Here we go. Let's go to some data here. And let's find a picture of me doing the paper symbol. This is one I did just before the talk. So I'm uploading this. Let's see what it says. It's not bad, but notice it doesn't say paper, which is what we want. So this doesn't work for us, which is okay. It's okay, because we're going to figure that out. So that's the option. You may not need to be that specific, but computer vision is there for that. So then the other question is, why does it keep doing it? The other question is, well, if that doesn't work, what can we do to do the rock, paper, scissors thing? Well, that's when we get into this notion of customized pre-built AI. So let's do a demo for that. So now you probably noticed that when we go to, I just went to the computer vision. Let's go back here. You hopefully saw there was this thing called custom vision, which is to customize and embed state-of-the-art. It's to customize a computer vision thing. And so what I've done is here is my rock, paper, scissors custom vision project. And you're going to see some images here. These are images that I uploaded literally this morning just to make my model work a little bit better. And so the idea is that you basically add images, and I already added those on something like that, and you give it a tag. And then you say, train. And that's it. And for us, what happens is it literally, like you can see I did this 40 minutes ago, right before the talk started, because I wanted to get the best model possible. And you can see I have like 138 scissor pictures, 126 rock, 136 paper, and 113 none, because it needs to know when nothing is happening. And what I've done is I've taken this model and I've made a little application that you're seeing right here. So let's go to CD. And by the way, this code's all available. It's here, and you can see that it's all literally right here. And what this is there's an API, a back end, and then there's a front end, right, to run the model. Now, you remember that what we said before, and this is important, is that the way it worked is we create this API in the back end, this for inference. This is what computer vision was. And then you have your actual app. And it needs to call an API over the cloud and then get a response. And now this is not slow, but it's not like fast. And if you were to send over like requests like every 100 milliseconds, this is going to be like, hey, sorry, you can't call us that fast. But I wanted to make it so that like the computer would look at me and instantaneously know, is it rock, paper, scissors? So let me show you how we did that. So here I'm running the back end. This is me doing the test. And here is the front end that's running. So I'm going to copy that. By the way, the front end is here. It's a Vue application. You can see it's all here. It's something that I wrote. It's artisanal, free, homegrown artisanal. And what I'm going to do is I'm going to open up a browser and put this up. Okay, and now you're like, Seth, you made the ultimate mistake here, buddy. You cannot use your camera while you're using your camera. That's why I have two. Boop. So now you're seeing me in real time. Look, you see me in the WebEx, and the other. It's the same camera. Well, it's two different cameras, but you can see it's like. But notice that right now it's like you're not doing any symbols, Seth. I'd be like, well, what about now? What about now? Woo. That's bananas, right? Oh, it's having a problem. There, you see that? It thinks those are scissors. So let's give it examples of the right thing. 1, 2, 3, 4, 5, 6, 7. And let's give it to custom vision automatically. Okay. There it is, sending data. So if I go back to the training images, you'll see, remember these things that we just did. And now all you need to do is hit train. Now this training process takes about 9 minutes, so I'm not going to do it. And what I did this morning is because this microphone is new, I wanted to give it pictures of me with the microphone so that it wouldn't get confused. But notice it still got confused, so we just give it more pictures of the right thing. And now you'll see that it's very fast. And you're like, how does it do that? And notice the updates are happening every 100 milliseconds, right? Now, this is really cool. Especially, for example, if you want to make new interfaces where maybe someone can't type and you can turn their camera on and they can control stuff. This is cool stuff. And you could do a ton of stuff. You gotta be wondering, because notice I'm not making an API call to custom vision. So the question becomes, how did you actually do this so that it's this fast? I'm glad you asked. Because it turns out that the stuff that we build, whether it be cognitive services or custom vision, is we have this ability at Microsoft to lift and shift down to on-premises. Like, for example, that computer vision stuff you saw, you can do it in containers and bring those containers down and have it work locally, which is cool. This one is also cool because you can actually download the image. You can download the actual models. So I'm gonna download the Onyx model just to show you what's in it. So it's building it. Let's download it here. There it is. Let's open it. I wonder what's inside. Look at this goodness. So let me minimize all this because I want us to see what is actually inside of this thing. So let me make a new folder on my desktop here. By the way, any questions? Questions as I open this up? We move the model over so that it's inside of a okay.
You might come to this later, but I'm just wondering where the boundary is between what you're doing where you're automatically uploading and it's detecting itself, and where you have to categorize, introduce different categories and mark up what it is that you're interested in.
That's a great question. So to repeat the question, when do you actually, what's the pre-work that has to happen is what I'm hearing. So what I was doing here is you can see that, like, if I hit space, I'm selecting none. If I hit space, I'm actually giving it the picture and the label. And then when I give it to custom vision and do a train, it's basically taking all of these images and retraining because it knows that this rock stuff that I just did, that is categorized as rock. So the boundary becomes, I basically, like, you can upload the images here, but I basically made an application in the API in the back end that pushes these images to Azure Cognitive Services Custom Vision. And so basically this API takes the pictures that were grabbed from the browser, pushes them to the back end. I get the training API client, and I just say, these are the desired tags that I have. I make sure that the actual tags are represented in the service. So So I might add another one. If I want to do new pictures, I can totally do that. And then for each of the images, I just add them and push them up. But it doesn't train it. I can do another API endpoint where it trains it, and I could probably figure out a way to download it and put it. But this model that I've downloaded, and this is where I wanted to get to, the model, it's something you can download. Now, I don't download it in this, but I want to just show you what it looks like on the inside. So let me Visual Studio Code in here and show you what it is it's actually exported. So notice that this is the model that we exported. These are the labels, more metadata properties. And this talks about like, what do we have to do to get the image into it? Because notice that it's not like give it any image. You have to give it an image at a certain size, 224 by 224, and it has to have 3 channels in this format, RGB 8, right? And so that's how that works. And then the license, you're probably wondering, well, crap, now I have some crazy license. Yeah, look, this is happy license. And then there's this question of what's inside the actual model. I'm going to open the model. Like, what is this? This is the actual machine learning model, which again, remember, is a function. It's a function. In comes the picture. And you're probably wondering, well, what the heck does these numbers mean? Well, 3 channels, RGB, height 224, width 224. And literally what happens is this thing starts to get multiplied by numbers. Well, this is a normalization, so this thing starts to get multiplied by numbers. Like literally all the pixels get multiplied by this number matrix. It's a convolution. And then this gets added to it. And then it goes through this other process. And then it goes through this other process until it gets all the way to the bottom. And out comes this vector of size 4. And you're wondering, well, what the heck does that vector of size 4 mean? Well, turns out that this one represents none. This one represents rock, for example. This one represents paper. And this is an example. I don't know if that's the right order. And then scissors. And it turns out that there's numbers in here. A, B, C, D. And it turns out that if you do the max index of this thing, it tells you what the answer is. So if A is the largest number, the answer is none. And that's what's happening. And the machine learning process is basically finding the best numbers to do that. It literally looks at your data and tries to make you happy. That is why if you give it images, right, it's going to be biased to the images that you give it. Example, this machine learning model is incredibly biased against Seth, right? And I don't know about you, but I don't look like other people. And so if those other people were to use this, it might not work. And that's where the ethics of AI come in. But there you go. This is the model. For us, we actually need to make it work in a browser. And it turns out that nothing in software engineering is real until there's a way to do it in JavaScript. There it is. TensorFlow.js. Bananas. If I were to open this up, you'll see that it's all in there. Bananas. And what I did is I just literally copy and pasted that into the client public directory. Bananas. And so this is all running in the browser, directly in the browser. And you're like, well, how does it do it? I'll tell you. Notice that when the let's see here. When the, I don't know if you don't know Vue, that's okay. But there is a life like an event life cycle for Vue, and mounted is the first thing that happens when it's mounted. And basically what I do is I say load the model. JavaScript has come a long way. I mean, this is looking almost C#y except for that my braces are on the same line, opening brace on the same line. So let's go to the load model, and you can see here, I'm literally loading the model from the browser on the client side. I'm loading the manifest and the labels, right? I'm putting these labels into the memory, and then and this is the cool part, I'm setting the interval at 100 milliseconds, and every 100 milliseconds, I want you to predict what it's seeing. And what it does is it gets the picture. You can see that it gets it right here. The size isn't right, but that's okay, because Custom Vision has a client library that you can use called Custom Vision TFJS that will resize it for you. Otherwise, you can do other things, like you can clip it or do whatever. But notice that here is the prediction, and this happens every 100 milliseconds. I get the 0th answer, and then what I do is I get the model labels and I get the max index, and that's it. And you can see right here, it's still going, by the way. You can see that's what's coming out. And so if I go like this, and you're looking at this and you're like, but Seth, how did it know this? I trained it with this one, remember? But it turns out that it was able to generalize, which is really cool. And that's how, my friends, that was done. This code, incidentally, if you're interested, github.com vision. What? Oh no, there's dependencies. I need to fix that. Joke's on you. Everyone can see it in here. But yeah, you can see there's a client. This is a little out of date. So if you have questions, just put some issues in. Looks like I have some issues with some stuff. Yeah, that's cool. Okay, cool. And again, it's really cool. And I think I even have like a GitHub action to do CI on it. I mean, this is cool. The build.yaml. There you go. It's cool. Okay, so that's that, and that's this. Now the question then becomes, well, what's the third way you were talking about, Seth? So that was the third way. So let's see if this. Let me get this out. So that was Custom Vision, and we did that. This is the example I did. So now let's do Custom AI the third way. Now here's the thing, and this is why I stayed up late last night, because this demo, I have a custom model that I built for tacos versus burritos, which is what this picture is right here. But I decided for you, dear friends, that I would go the extra mile and download these pictures from Custom Vision and make my own custom model. It turns out that the typical process for building these models looks eerily similar. You have to go through this whole process of training the model, making sure it works, deploying it, monitoring it, and then going back. This process developers know as DevOps. But for machine learning, it's called MLOps. And it turns out that training a model, and I'm gonna open up the one that I built. So I can stop this here. I can stop this here. And I thought I would just reuse some code from the tacos and burritos. So let's go there, food AI, and then we'll do code dot. And I'll show you what it looks like to build a model from scratch. Okay, this, yes, it's still loading. So this is PyTorch. I'm a fan of PyTorch. Now I do talks on PyTorch, but this is not what this is for. I just want to give you a sense for what it looks like to build these things from scratch. So basically, with PyTorch, you have this notion of data sets, data loaders, and transforms. And this is for getting data into the machine learning model. The data set basically that I'm using is a image folder. And the image folder that I used in this case is I did this for tacos versus burritos, so you can see that there's. Oh man, I hate it when I do this. So I need to minimize this because there's too many tacos and too many burritos. Basically, I pass in the training and the validation data. Right? You can see train, validate. And I have two data sets, one for training and one for validation. Now, the question is, well, what's the difference between the both? Training is what you put into the machine learning model so it can optimize the numbers that we were looking at. And the validation set is to test whether it does a good job or not. So if you hear about a machine learning model getting 99.9% accuracy, it's not 99.9% accuracy on all the pictures in the universe of tacos and burritos, but it's all the pictures that were held out during training, and that's important. So this is the training data set. This is the validation data set. This is the actual machine learning model. And it's basically a sequential model that borrows a different architecture, this case MobileNet. There's others, like, for example, ResNet. There's VGG style models. And the question is, well, which one do I know? How do I know which one to use? You don't. It's data science for a reason. You have to guess and check, which is basically what science is, but with more formal processes. And then you have this measure of how bad we are at it. This is called the loss function. And this is called the optimizer. And the optimizer's job is to look at the loss function with respect to this function and minimize it. And then it does it in a loop. And I didn't know beforehand, like, which one was going to be a good model or not, because I had never tried it. So what I decided to do is I decided I don't have a lot of computers at home on a GPU to run these things. I guess I don't need this, unless you want to get like two Seths. So why don't I just run this in the cloud at the same time? And that's what I did. You can see here, this is Azure Machine Learning, where you can build your own models. And you can see that I did my paper time model. Let me edit the columns because there's some of them that we just don't need. Let's take that out. Let's take that out. Save. And then let me save the view here. And this is cool. Like you're seeing me do like DevOps, but for machine learning. And what you see here is how long each one of these took to run. Do you see it? And if I would, this all happened in parallel. This means that this all took 24 minutes. If I was to do this in like on my machine, it would take all of these minutes together. Notice that I was able to describe like the model type that I was, let me close this so I'm not bogging down my RAM. The model type I was using, I can actually go into the experiment itself. I can see the loss, the accuracy. I can like, you're like, but Seth, if you ran this, then how do you even know what it did? Well, it turns out I can see exactly what it did. Exactly as if it was running on my machine. This is super cool. You're like, well, what about the models, Seth? These are all the models that it built. Because I checkpoint my models as it's building them every time. Right? And so now I have this ability as a person, you know, because, you know, like working on stuff by yourself is easy. Once you start introducing other people, because look, software is easy. It's people that are hard. Same with machine learning. Now I have this ability to actually like run stuff together. And this view I created myself. So it looks like there was one that had the best accurate 92% accuracy. And I got to figure out, I think it was VGG 19. So let's go to the VGG 19 one and let's look at the metrics. That's nice. But let's go to this. Yeah, looks like this is the one that had the best. Reset that. This is the one that had the best accuracy. There it is. Yeah, look at this, 90. And so now I know that this is the model that I want to use. And it turns out that you can register these models as well. There's the VGG 19 model. And so now when I go to this particular model, I have a model, right, that was created by me with PyTorch that has all of this information. And now instead of like as a data scientist, and this is a problem with data scientists that I know we have, we're like programmers from the 90s, like maybe mid 90s. You know how we used to email, and those of you that are old enough here will laugh. Those will laugh because they're like, it's true. And those of you that are young enough will laugh because you're like, that's dumb. We used to email code files to each other. Yeah. And then we like got this thing called source control, and we thought it was the greatest thing ever. But it turns out that source control for machine learning is different because you need your data, you need your models, and you need to know like how good were your experiments, right? And that's what this is for. And so that's what this whole thing is. It's really cool, but that's the way to build custom models. Okay. So what I did is I actually went back and did this for rock, paper, scissors. And let me show you what I did. So we don't need this here. Let's go to cd dot rochambeau code dot, and let me move this over because I want to make sure that there's not stuff in there that you are going to be able to see. Okay, cool. Okay. So what I did is I literally wrote some Python code to download all of the images and put them here, right? Because I did the tacos and burritos thing, and you can see there's the pictures that I literally just did. The tacos and burritos thing. And what I did is I reused this code that did tacos and burritos, and I, instead of pointing it to data, pointed it to Rochambeau, which had these training and validation. And this all just worked because apparently I write code that's reusable. And then what I did is I just had to pass it like, let's see here. Here. Instead, I just had to pass it like the data to the right spot, and it worked great. And that's what I passed in. And to run this in the cloud, I basically just had to pick my compute, pick my data store, put the script parameters. Remember how I did it locally, and then I submitted it. And I did one for a model. I tagged each one the way I wanted to, and that's where I got this gloriousness. By the way, it's never all green. Obviously, I made it so it looks nice. If you want to see what it actually looks like when you're doing actual stuff, you're going to see more like this. I'll close this. Things that fail, things that aren't good. Just like, look, if anyone ever shows you like a DevOps pipeline that works 100% the first time, they're either like a witch doctor or we should make them president of the universe. None of this crap ever works the first time. But it did for this demo, but I wanted to tell you that it's not like that, okay? All right. So I repurposed my tacos and burritos and fed it images that I sucked down from Custom Vision, and that's where we have. Okay. So to recap, machine learning and AI are very useful. You got a sense for when it is good to use machine learning. We looked at this from the perspective of computer vision, looking at pictures. There was 3 options. Number 1, just use computer vision. It probably solves 80% of the problems. So just use it. It's an API that you call. In our particular instance, it turns out that it's not programmed. The models are not there to recognize rock, paper, or scissors. So we went the route of custom vision. And custom vision worked great for us. And we also were able to download the model and put it inside of an application that literally runs in the browser. Now, if that wasn't able to work, if we weren't able to make that work, then we could roll our own model using Azure Machine Learning Services. Now, the part that I did not show you is, just like before, it produced a model that was registered, and then we could make an API out of that, or we could download it and run it in the browser like I showed you before. How would you do that with the model that I used? In my case, mine was specifically on, let me go back. Mine specifically created these things called Onyx models. Onyx models are interesting, but again, as with all things, it's not real until there's something that runs in JavaScript. Turns out you can run Onyx models in JavaScript as well. And it turns out that it's super fast. Super fast. And so if I were to build this demo out further, I would use Onyx.js. Now I didn't use TensorFlow.js. I used TensorFlow.js just because it worked out of the box, and our second option was the best option in this case. But then later on, if I wanted to build a custom, I could use Onyx.js. What would you get if you did both hands? Good question. Let's just run it and see what happens. I think in this case, I can just run the client since we're not submitting stuff. So we'll yarn serve this. Okay, so that is the end of my presentation. Here, let me put this here. If you want to get some, I would take a quick snapshot of this, screenshot of this. This is where you can go to the docs of the stuff that I built. The food AI model is the one that I showed you. This is just a github.com. This is the one I just repurposed for doing. You can see it's all in here. There's the training stuff. Right, everything's in there, so you can take a look at that as well. So the question was, what happens if you put both hands up? Now here's the thing. I want you to be I want you to know exactly what's happening. Again, this model is only trained to generate a vector of size 4, wherein the max index tells you none, rock, paper, or scissors. So this thing right here is not a probability in the mathematical terms. It's basically what happens is, in our case, and it does this in the, let's open the model. Let's open the Onyx model here, so you can see it. Since this is the actual model that we're using. At the end of every one of these things, let's go to the bottom. There's generally something called it's just an argmax in this case, but there's something generally called a softmax. And I don't know if it does a softmax in this case. Here it does an argmax for there it is, softmax. I knew it was there. Now this is an interesting function. Basically what this does, so the last thing that happens is there's a big matrix that's multiplied by something that's 1024 by 4, and out comes this vector of size 4, and then this C is something that's added to it of size 4, right? So this is called GEM, or generic matrix multiply, with a bias addition. The softmax forces this vector of size 4 to sum to 1. It's just mathematically forcing it to sum to 1. The reality is that the answers that come out of these are just numbers. They could be big, medium, small, it doesn't matter. The softmax forces it to be to 1. So these things aren't real probabilities. They're basically a softmax function over the output of the final generic matrix multiply. So if I put 2 hands up, it says paper, but it's not going to say 50-50. What it's going to say is it's going to be like, well, I can only guess 1 or 2 things, and it's here. But I bet if I do something, well, the model is so good that it's okay. Do you see how I'm doing this? It's like getting confused because it doesn't know. And this little V thing it's probably learning that. I don't know if that's the case because I don't know what it's learning. But if I put both hands up, it's going to say paper because of that's how it learned. And in this case, the volume of the weight of the numbers that end up in the final vector mostly accumulate in the paper. Great question. All right. Any other questions? We have a couple of minutes. And feel free to take yourself off of mute if you're so inclined. Let me get this slide up too so y'all can get the things. Well, my friends, if there is more questions, feel free to @me in the Slack, since this is going to be since this room is going to be over at the end of this session. Just @me on the Slack. This conference is still going on. I am available via Slack. Just literally ping me, just like I would be if I'm at NDC. I'm so glad you could come. Hopefully this was useful. I find it's useful to understand as a programmer what this actually means, so that when you are building these things, it makes sense. And now a final word on the ethics. These things, while you're looking at it, makes it feel like it's thinking. It's not. These things do not have any emotions. They don't care. Their only goal is to satisfy making your data minimize the loss function. That's it. And it turns out that for humans, whenever we see anything that feels human, we anthropomorphize it. Like, take a rock, if you put a smiley face on it, you're like, oh, it's happy. No, it's a rock. The biggest social ill that could happen from AI is anthropomorphizing it, because what it does is it shifts ethics blame from humans to the computer. And when we do that, everybody knows what the answer is. And so it's important to use these things ethically. All right. Thank you so much for your time. We ended right on time. Thanks for coming.